In this video, I will be talking about solving exponential and logarithmic equations. There's basically three key ideas here. There's a number of different ways this works out. So I have actually 10 examples, which is more than I normally do. But really, there's three key ideas. And the first one is how to approach an exponential logarithmic problem when it's the same on both sides. That is, the exponentials on both sides, or we're going to see one here where there's logarithm on both sides. It's technically the same as what you do when there's different sides, so logarithm on one but not the other, or exponential on one but not the other. It's technically the same underneath, which I'll unpack when I get there. But it it feels a lot different. So I included two different categories. The last example we're going to do is quadratic form, which is an idea we've seen before when we did polynomials, but I'm going to unpack how to do that one as well. So I've got my 10 examples, and I'm just going to get into it and kind of talk about it as I go. Now, your book likely makes a big deal about the fact this works because these are one-to-one functions, which means there's only one answer for any given x value. And then each x value has exactly one answer. And sorry, for each answer there's exactly one x value. So this is why you can just kind of cancel out both sides. But the trick, if you have an exponential on both sides, is the first thing you want to look for is try to rewrite it so that both sides actually have the same base. If you can rewrite them with the same base, you can just kind of cancel the exponents, which is of course preferred to other ways of approaching this. So 4 to the a plus 2 equals 16 to the a minus 3. So what we're looking at here is same on both sides mostly. The bases are different, so we need to make them the same. You could rewrite both of these to powers of 2. 4 is 2 squared, 16 is 2 to the 4th power, but 4 squared is 16. So we can write the 16 as 4 squared, and then we've achieved the same base, and that's probably better to go with the largest common base, just because it's less work later on. Now, power to a power is one of our exponent rules, and you're supposed to multiply. So this becomes 2a minus 6. So 4 to the a plus 2 has to equal 4 to the 2a minus 6. Now, because exponential functions are one-to-one, if the answers are the same to these two, then the exponents have to be the same. If the power evaluates to the same thing and the bases are the same, the exponents also have to be the same. So technically, you're using a logarithm on both sides to cancel these out is a reasonable way to approach it. But logically speaking, it's easier to just think in terms of set the exponents equal to each other. So a plus 2 equals 2a minus 6. I'm going to subtract the a over to be with the other a, then add 6, and a is 8. Which is the correct answer. That gives me 4 to the 10th power to be the same as 16 to the 5th power, which is absolutely true because 16 is the square of 4. In our second example, we see 1/3 over here. This one is 1/81st. So again, recognizing the comment that we can readjust it, we can rename this this base 1/81st into a power of 1/3. It's actually 1/3 to the 4th power. So we're going to rewrite the base so that it's the same as the other base. And that gives me 8/3 over here. And if 1/3 to the b power has to equal 1/3 to the 8/3 power, then the exponents have to be, if the bases are the same, the exponents have to be the same. So this is 8/3. Oh, I got distracted halfway through and lost my alphabetical order. Well, halfway. Way back at the beginning. All right, log base 2 of 5 equals log base 2 of 10 minus log base 2 of x minus 4. It might be tempting for you to go through and cancel all the logarithms right now, but you can't do that because of the addition. Logarithm is not a type of multiplication. There's not a distributive property for logarithms, so we can't just cancel one from each term. We have to combine these, and this is why we learned to condense expressions earlier in this chapter, because if we need this to be one logarithm on each side. That's how we cancel them. So the left side already has just the one logarithm. It's good to go. we have to combine these into one logarithm. So since it's subtraction on the outside, I'm using the quotient rule. This becomes log base 2 of 10 divided by x minus 4. Now, because these logarithms are the same and have the same base, these are the same logarithm on each side, just like we did with the exponentials, we can cancel these. So the arguments, if the logarithms have the same base and they're equal, then their arguments have to be the same. So to solve this one, I'm going to multiply by x minus 4, which gives me 5x minus 20 is 10. So 5x is 30, and x equals 6. When you solve a logarithmic equation, you may produce extraneous solutions, typically in the case where sticking that number into one of the logarithms will cause the inside to be less than 0 or less, I should say, not positive. Because logarithms, their domain is positive x's only. In this case, we're okay, because we stick a 6 in here, it's still log base 2 of 2. So it's fine. In fact, that makes them equal because 10 divided by 2 is 5. So this is okay, but you should always check for extraneous solutions when you get an answer to a logarithmic equation, specifically that it's inside the domain of the original equation. So here I've moved on to my second type of problem. There's a logarithm on one side but not the other. Now this feels different, and so it's going to look different when I do it, although technically the proof that you would make for why what we did before works is going to be the same thing we're going to do here. The first thing you want to do is isolate the parent function. So we have this ln, and that's going to be the trickiest thing to get rid of. There's a 2 in front. I want to get rid of it. So I am going to divide both sides by 2. That's job number 1. Isolate the parent function. Isolate, in this case, the logarithm. Now I want to cancel the logarithm, which I do by doing its inverse. The inverse of a logarithm is an exponential. So I'm going to cancel the cancel the logarithm with an exponential. In this case, the base is e, so I'm going to exponentiate. That means I'm going to take ln of x, and I'm going to make it the exponent on an e. And I'm going to take the 9 and make it the exponent of an e, because e is my base. That's what ln means. On the left side, that's going to cancel. E to the ln of x. What power do I stick on e to get x? Well, whatever it is, when I stick it on e, I'll get x. So those totally cancel. And that's why we did it. And so my answer is actually e to the 9th power, for which you could produce a decimal approximation if you want. But since a monkey can use a calculator, I'm going to just circle x equals e to the 9th and let somebody else worry about what decimal that might be. 7 minus 3 times the log of 10x equals 13. So again, first thing I'm going to do is isolate my logarithm. So negative 3 log of 10x equals, I subtracted 7, so this is now 6. I'm going to divide by negative 3. Log 10x is negative 2. And now, to cancel the logarithm, I'm going to exponentiate. My base here is 10, so I'm going to make the left side the exponent on a 10. I'm going to make the right side the exponent on a 10. That's exponentiation. And it's going to cancel my logarithm. Now, I promised I would unpack this. Let's see, 10 to the negative 2nd power is 1 over 10 squared, which is 1 over 100. And if we look up here, when we did this to cancel out a logarithm on both sides, it's basically the same as this. It's just that since they're both logarithms, when I exponentiate, these both become exponents on a base of 2. They both cancel, which is why you expose the insides only. And the same thing is going to work out for these. If you use a logarithm on both sides, it's going to cancel the exponent. Going to cancel the base, I mean, with the power with the logarithm, leaving just the exponent exposed. So really, these are all using technically the same method. It's just when they're the same on both sides, it's easier for your brain to handle just by thinking in terms of canceling. In this case, I'll get back to this then. Divide by 10. That gives me 1 over 1,000, which is inside the domain. It's positive, so I'm good to go. All right, my last example here. You could proceed immediately to exponentiation because the logarithm is all by itself. So you could exponentiate both of these with a base of 5. The problem is 5 to the 20th power is huge. And then I'm going to need to take the fourth root anyway. So I'm much better off to use the power rule first to move that out front as a coefficient and then divide it. So I get log base 5 of x equals 5. And that's going to be much easier for my brain to handle when I exponentiate, because 5 to the 5th power is, oh, my answer. And then I don't have to worry about 20 and the fourth root and all of those things. Wow, 5 to the 20th power, that would have been huge. Okay. So yeah, you can, simplifying up front can sometimes help a lot. Technically, I could have done something similar here using the product rule to split this up into log 10, which is 1, and log x. Then I would have subtracted the 1. I would have had negative 3. 10 to the negative third power is 1,000. 1/1000th, I should say. So I could have used the product rule here if I wanted to. I didn't think it was as helpful in this case. The power rule is the one that generally makes things a lot easier. But anytime you think simplifying first might help, it almost never hurts to try. I guess it might hurt your brain a little if you go the wrong way. But look for the easiest solution. Like, that's a good habit. So here we have exponential, but only on one side. So we're going to cancel this exponential using its inverse, which is a logarithm. The exponential function over here is already isolated, the parent function. So there's no subtracting or dividing to do first. I just need to cancel the exponential here. So I use a logarithm. I use base 3 because that's the base I have. Log base 3 of 7. Although you're going to see later, technically we could do this with any base we like. It just means more typing. The advantage here is these cancel directly. So the x is left over. So x is just log base 3 of 7, which you should be able to stick into a calculator. So again, I'm not going to bother, but yeah, this one actually is quite quick because all I have here is this calculator step. Similarly, this one has just the exponential on this side. The base is e, so I'm going to use log base e, which I write as ln. E to the 2x plus 1 equals ln of 8. Now that cancels over here, leaving 2x plus 1. And to isolate x, I will need then ln of 8 minus 1. And then I'm going to divide by 2. So ln of 8 minus 1, all divided by 2. Again, you can stick that in a calculator if a decimal approximation is where you'd like to be. I am not going to take the time to do so. Here we have exponential on both sides. So it's tempting to try to cancel them, except that the bases aren't the same. This is one of the icky ones. I'm actually looking at these exponents and being upset about that too, but this is pre-calculus, not algebra 2. If the powers were nice, we could have handled this in algebra 2. So looking at this then, I could do log base 3, and that would cancel the left side directly, but the right side would have log base 3 of 2, which is yucky. I could do log base 2, which would cancel the right side nicely and the left side not so nicely. I'm just going to steer clear of trying to decide which of those is better and just do the ln on both sides because it's shorter to write, and I'm going to wind up with a mess no matter which way I go. Although, like I said, the base is immaterial anymore with calculators being able to do other bases. Traditionally, ln or common log were the ones we picked because they were the ones that had nice easy buttons on the calculator. Once you take the logarithm on both sides, these don't cancel because the bases aren't the same, but it does allow you access to the exponent using the power rule. So this is 6x minus 2 times ln of 3, and this is 4 minus 4x times the ln of 2. Unfortunately, I want to get this x over here with this x, but because of the multiplication over difference rule, I have to distribute. So this is 6x times the ln of 3 minus 2 times the ln of 3, and this is 4 ln of 2 minus 4x times the ln of 2. So when I put the x's together, I'm going to add 4x ln of 2 to both sides. I'm going to add 2 ln of 3 to both sides. Now here I've got my x. I'm going to factor it out, which leaves 6 times the ln of 3 plus 4 times the ln of 2 equals 4 times the ln of 2 plus 2 times the ln of 3. And I can divide by this. It's yucky. If you're going to end up with a decimal approximation anyway, you could put all these into decimals right now and then let your calculator do the heavy lifting. Just be careful to leave a couple of extra decimal places when you're doing your work so that at the end you can round appropriately without causing a loss of precision. If you round at the beginning to like 1 decimal place, then you're going to accumulate more error than your teacher might be comfortable with. So I'm going to change this into a power. 2 to the 4th power, that's 16. So that's the ln of 16. This is ln of 9. 6 ln of 3. 3 to the 6th power. 3 to the 4th is 81, so that's 243 times 3 is 729. Wow, that's awful. And 2 to the 4th power is 16. 4 squared is, yeah, 4 squared is the same as 2 to the 4th. That's interesting. So I could stick that in a calculator pretty easily. Although, again, I don't really see a reason why I should have to. If you really wanted to, you could add these together. 9 times 16. But, again, I don't want to. So, depending on who your teacher is, there may be some other forms that are preferred. You know what? Okay, I'll break down. I'll stick this into a calculator and get a decimal approximation. So, the top is ln of 16 plus the ln of 9, and the bottom is the ln of 729 plus the ln of 16, which is 0.53. So it's a big mess. Rounded to the nearest hundredth, 0.53. Which is different from what my book has. Now I'm concerned. 3 to the 6th power, 729. 2 to the 4th power was 16. 4 to the 2nd power, 16. 3 squared is 9, right? What did I do wrong? I'm going to pause this while I figure out what I did wrong. I found out what I did wrong. I copied down the problem wrong. This was supposed to be 6x minus 3, which is why the book has a different answer from me. I'm pretty confident this is right. Phew. Turns out, I mean, their answer was as yucky as this one, just a slightly different number. I won't make you do too many of these, I promise. So this last one looks different from the others. This is in what we call exponential form. Quadratic form. We did quadratic form with special patterns in polynomials, and the trick is to recognize when you can factor a trinomial because it follows a pattern. If you think about it, e to the 2x by our exponential rules is e to the x squared. So this follows our basic quadratic pattern, although the number that is in the quadratic, or the variable I should say, is e to the x rather than just x. If it makes you more comfortable, you can do something we call u substitution, where you take your e to the x and change it to u's. I mean, you can pick whatever letter you like. So if you prefer, I wouldn't use x's in this case because you might cause confusion between what x is and as opposed to e to the x. But you can pick whatever letter you like, really. But if you remember that e to the 2x is e to the x squared, we just let u be e to the x. You can see this is quadratic, and you should, if it helps you to factor it that way, you can rewrite it with letters rather than exponentials. Let's see, this will be u and u. Multiply to -2, add to -1, that's -2 and +1. So what we have here is e to the x minus 2 and e to the x plus 1 has to equal 0, which gives us then two possible solutions. E to the x minus 2 equals 0, or e to the x plus 1 equals 0, which means e to the x could be 2, or e to the x could be -1, which is actually a problem because if you paid attention when we were doing exponential functions, you should hopefully remember e to the x has a horizontal asymptote at 0 and its range is positive numbers only. So there is no way for e to the x to equal -1 using real numbers. So this has no solution, this part, I should say. But e to the x could be 2, and to solve that one we use ln on both sides. So that cancels x equals ln of 2, and that's our solution. So there's no solution to this line of reasoning here, but there is a solution to the equation at large. It's ln of 2. So splitting it up in if you recognize this form, it's quadratic form. So rewriting it so that you can factor, or really if you're comfortable with it, you can just factor it using the e to the x's. And then solve, since it's equal to 0, if it's not already equal to 0, you got to make it do that before you factor, don't forget. And then solve each one separately. Although remember, exponentials will never come out to a negative, I should say a positive base. There is no exponent that will raise a positive. There is no real exponent that will raise a positive base to a negative answer. Those are all 10 of my examples, and my lessons video is already pretty long, so I'm going to stop here. I guess I'll just wish you luck and then stop.